So now it
Okay.
should be recording for me. Should be getting all those. So I'm going to share my screen and kind of go through what I did for my steps. This is me figuring out the math for my feed. This isn't actually the entire simulation. So if I remember right, there was water, there was ethanol, acetone, I can't spell today, O-N-E, then butanol, I think, and butanol. And so this is butanol. It's another one of those compounds that you might want to use find if this isn't specifically N-butanol, right? Because there's two different butanols. You could have one or two butanol. But because it says one here, we know this is the right one, but maybe in the future it would be good to specify. So I think I used NRTL in my base method. I could be wrong, but it's kind of irrelevant for this first part. So we're all good. It wants us to click on our parameters, make sure they're all loaded in. They did. I will run my analysis setup. Okay. Yeah, this acetone thing comes up a lot. I'm not really sure why this is such a problem. He said just to ignore it, that our data should be fine regardless. I don't know how to feel about that. I feel like there's a reason for it, but I am just going to roll with the punches. So in our end feed, he wanted us to have a very specific, it's ABE fermentation, acetone ethanol butanol fermentation, so which is actually pretty common. It's how we industrially make butanol. So the easiest way I found to do this is to separate the original feed into two streams. So we have water, organics, and I'll just say this is what the feed would be, right? So in the original homework, and I can actually just pull it up. Let me find it. 1 second. I think it was a 10,000 kilograms per hour, if I remember right. 10,000 kilograms per hour, and 3% of that was weight percent was water. So for the amount of water in our feed, we know it has to be 9,700 kilograms per hour of water, right? And I'm just going to select that here, right? And this is going to be in, what is it? 25C118, no, 1 bar. So 25C bar. So this is the water stream that's been specified. And this is the important part here, organics. So we know that if we have 10,000 kilograms per hour and 38% of it was organics, we know it's going to be 300 kilograms per hour. So what I'm going to do is under total flow rate, I'm going to specify, first I have to say it's in mass. It's going to be kilograms per hour. And then I'm going to say, actually, sorry, 3,000, if I remember right, 3,000. No, 300, sorry, 300. Now, the nice thing about Aspen is you can specify total flow basis in mass, but your composition in moles, which is pretty convenient. So I went to mole fraction, and it wants it to a 3:6:1 ratio with acetone, butanol, and ethanol. So we're going to say acetone is the 3, butanol is the 6, ethanol is the 1. So that's it. So we're going to do the same thing, just 25C, 1 bar. Okay, we're going to run it. We have to get our block set up here. Okay, check, ready to go. Run it. All right. Taking its jolly sweet time. All right, come on now. Well, that's bizarre. Okay, come on, Aspen. Okay, well, in short and sweet TLDR, doing this, you've specified your inputs, you know how much water you put in, and this is a way to specify the mass flow of your organics in the feed, because you can look at the results for your feed and see the mass flows of organics as well. This is just the way I did it, just to make it so I didn't have to calculate this all by math. I could use Aspen to do it, and I don't know why my simulation is just kind of TKO'd itself. I'm not sure if that helps very much, Jenny, but that's the way I did it, and I just wrote down the mass flows for each of my components out of this feed stream here. I found that was enough for me to get my the mass flows for in the end. Really, you probably could actually just give this entire system in your original simulation and then connect this feed to all the rest of your parts. But the problem about doing that directly is that when you actually mix these organics, just pure organics stream with water, it actually goes up about 1 degree Celsius because of the heat of, I think it's the heat of mixing. It releases a little bit of heat, so it heats it up. What you could do is then you could just cool it down to 25 again and then proceed that way, but that's just another step. And I'm going to close my Aspen out because I don't think this likes being alive anymore. How do I do this? Task manager. Is there anything else you want to go over, Jenny? We can also do the exam stuff. You know what? I think I'll just. Hey, Ruben, what do you want to go over? Do you want to go over exam, or do you want to go over the previous homework?
Yeah, if we could go over the exam. I haven't looked over the practice exam yet, but
Okay, let me stop my sharing here, and I will.
he's like, what exactly he's trying to test. He said like, if you were able to follow through today's lecture, then you should be okay. But I don't feel like that's 100% true.
Let me find old exams, and we looked at this. I looked at the exam while he was doing lecture today, and kind of got a feel for what it is. Let's see. I will share this screen here. Exam 3. Can you see my Chrome?
Oh yeah.
Okay. They're just kind of this format. So what are like technical aspects of Aspen itself, and then later on it goes into some like what would you do here scenarios. But this is just like for molecules, right? In your simulation, do you have to do it? You have to have all of them, just some common ones, but like they don't need to be added, or do you have to just like that will just do it for you, right? And as we've seen using Aspen up until this point, that we need to specify every single thing in our simulation. Every single part or aspect of any compound has to be specified in Aspen in some form, right? Everything we've used so far. So not if it was ionic species, solid species, water, ethanol, acetone, butanol, everything had to be specified. So this would be added explicitly.
Yeah.
We can, I think what this also means is it's just saying in the components eventually. We've seen in the past, and this is actually here, if ions may or be present in your simulation, we use the electrolyte wizard, and that is actually we have to use the electrolyte wizard. Because I've learned this through a lot of trial and error, unfortunately, a lot of time spent not trying to figure out what went wrong, that if you don't use the electrolyte wizard, Aspen will not pull the right dissolution information from its databases. So, we have salt, we have a specific amount that'll dissolve over, say 100 grams of water, right? If
Yeah.
we don't use the electrolyte wizard, it won't pull from the right source, or it'll pull the wrong thing. It's just really complicated, right? We can manually add our ionic species, that's fine, but we have to use the electrolyte wizard to get the equilibrium data from databases. So that would be, we have to do this one because we can do it by hand, we can add them, but it won't determine their behavior by itself. And then here, that's just not right.
Yeah.
So for 3, Aspen works with. We can actually do any you want. You can create your own set of SI units, which I've done. I got tired of switching like kilomoles per hour into moles per second if I was doing something. So you can make your own specified unit sets. I find it's pretty easy because that way you don't have to. If you know you're going to be using atmospheres a lot and a specific mass flow rate and a specific mole flow rate through the entire simulation, you don't want to keep changing it as you're working. You can make your own set, and it'll make your life a little easier. So that would be B. And we've seen before, Aspen kind of works in 2 different areas. We have our properties environment, and then we have our simulation environment. Properties is where we've set up all our components, our property methods, interactions, chemistries, all sorts of things. So we can see the solutions that we know that's in our simulation environment. So that's out of the table. Phase diagrams is PX TX diagrams. We've actually done this in class. So we know that's good. And then define compositions of feed streams. Again, we've seen that be for our simulation environment. So really, it's only B. Oh, hey, Joseph.
What's up?
We're just going over the exam stuff.
Cool.
We went over the first 4, and also I'm gonna put this out there that like I'm like 99.5% confident in all this stuff, right? I've used Aspen for quite a while, but I will say that I'm not Dr. Fromm. I have not used this for 30 years, so this is just the best of my ability. But some of these are pretty give and take. Like this one, you know for a fact that you can't just only use SI units, and we can't. That just doesn't work because we've used SI units before. So go on to 5. So we've done our properties environment. Now we're doing simulation environment. So it's most suitable to execute non-steady state simulations. Well, we've seen that we actually have to use a separate piece of software to do this, Aspen Dynamics. So that's not going to work. Steady state simulations. Okay, that one we know that we have done and does it well. So we'll keep that on the table for a second. So simulations where feed streams and some in-process streams are specified by the user before starting a simulation. Show feed streams. I don't. This kind of confuses me. The wording between these two, because the steady state simulations, it's true, right? I'm not really in process. Oh, I get it. So I think what this might be saying, or this might be trying to say, is that like maybe some things are happening inside the streams before the starting simulation. We have to specify everything in simulation. I'm gonna guess it's B, but I would ask him to clarify that in the exam. What he's trying to get out of this. I think it's B, because we've only done steady state simulations. We can do semi-batch simulations. I found there's actually a batch reactor. It's pretty garbage actually. It's not good. And then non-steady state, it's just an absolute nightmare. I would say probably B. So for material streams to be specified before the simulation are, well, because we usually do sequential modular, we have to start with the feed and work our way up. And we've seen that the only thing we have to specify really is the feed. I think there's actually a way to make it so you can, let's say you had a mix, so you have 2 streams in, 1 stream out. I think there's actually a way to specify 1 feed and 1 product stream, but that's a little more complicated. I think for this, he's looking for feed streams only, but I'm pretty sure, yeah. Sequential mode is only selected in special cases. The default mode for simulations are used in batch processes only. This is actually the default. So remember, we have really 2 modes: sequential modular and equation oriented. Sequential modular is the best for if you specify your feeds and you specify the operating conditions for all your blocks. Because what it'll do is it'll basically solve 1 block, then the next, then the next, then the next, as we continue down the list. Whereas equation oriented, if we have something like a recycle stream, it will just basically solve like a really complex set of math. You can kind of see sometimes that there's a little bit of error in your answers. It's usually pretty small, but it's there. Sequential modular is, if you're specifying feeds and specifying operating conditions, it's pretty much exact. So for 8, tabulate results of your simulated streams are accessed through, what do we got? Table you must generate by hand after simulation. A folder in the properties environment, a folder under result summary. Well, we've seen that result summary, there's that streams file we can look at. In the properties environment is only for the setup, so it would be under, it would be C for result summary. 9, sensitivity allows determination of the number of tubes in a heat exchanger, locating flash units, varying a parameter of the simulation over a wide range to see how this impacts other parameters. So we've seen that we can actually use this for things like how much mass is in a vapor stream, all sorts of change one thing and get a couple answers out. So it'd be C for changing, varying a parameter. And even in our sensitivity studies, there's actually a vary tab where we actually have to define what our independent variables are. And then in the define tab, we have to define what our dependent variables are. So 10, utilities are specified as components, specified for many blocks if that is desired, only applies to heaters. Well, we know that this isn't true, because we actually can give it utilities for things like flash drums. So with anything that really takes heat, we can do that, because we can specify the heat comes from high pressure steam, or the heat comes from, we could have a gas fired separator. We could also have things just with straight electricity, right? So we know that's not right. Utilities are specified as components or specified for many blocks if that is desired. Well, we know that we don't actually have to specify utilities. All the energy requirements we're given in Aspen is heat duty, which just basically means that the amount of energy it needs. What source that comes from, we can define under the utilities tabs for all these blocks, but it's not necessary. So I would say probably B. Because when it says as components, we're only doing molecular species and components. Utilities is actually its own separate folder. Now we're on to part 2. All right, and I'm going to guess this is going to be a lot of what the exam is going to be like. And since we have Aspen with us during this exam, I'm going to guess it might be a little more technical. It might be like if you were to look for where you could, find the temperature of your feed stream, what would you do to find it? It's going to be a little more technical, I'm going to guess. This seems like things you could memorize or have, in the back of your head, no matter what. I think he's going to. What's up, Joseph?
I thought he said that he doesn't want us to use Aspen while taking this exam.
Does he not?
Yeah, I'm pretty sure he said that last time because not everyone can access it, and he can't guarantee that all of us in the class can access it simultaneously.
That's true.
Yeah, he wants it to be as much as like it would be in the classroom as possible. That's why he's having,
Got
Zoom
it.
on with the cameras on too.
Oh, that's right. I forgot it. Yeah, I guess I missed that. Yeah, I'll keep that in mind. Then it'll just be just like these problems. Then this level, I'm gonna guess if this is the last year's exam, this is gonna be, I would say, almost a carbon copy with the little things here and there changed. This is gonna be probably exactly what you're gonna see. And
yeah, he said it wasn't going to be harder than this review.
Yeah, and if you're using Aspen, I mean, if you've done the homeworks up until this point, he's right. You're gonna be good because this is just, have you used it, right? Do you know like where you specify your material streams? Do you know how to get your results? I mean, it's, if you've done the homework and you've done the work he's kind of put forward to you, you'll be fine.
I feel like it's too good to be true because these questions are pretty. If you have done the homeworks, you should know all this for the most part.
Yeah, this is the old exam. This isn't like a practice thing. This was it looks like the old exam he gave. So I can't imagine that this year he did any more than last year's. So that's good.
Sweet.
Cool. That'll be a nice exam. And I know that he's still dropping an exam without having the final as well. So
it's only going to be the second and third exam that are going to be towards our like exam grades.
He's just going to drop the lowest one. So let's say you on 2 of the exams you got 100%, and then the third exam you got you absolutely flunked it.
Yeah, I tanked the first one, so I was going to ask him if he's still dropping one because I definitely need that one dropped.
Yeah, I think he said, I'll double check afterwards, but I'm pretty sure he said he's still dropping an exam. I think the vote we took was just on not having the final.
The final.
Yeah.
Yeah. Okay.
So that's why it's kind of like amazing just to think that we'll just get to drop one entirely and not have to even think about it.
It's awesome.
So let's do problem 2. Excuse me, my throat. So circle in the screenshot below and label as indicated below. There are multiple correct options. Circle and label only one. Example for circle and label. Thanks, Dr. Fromm, just in case I couldn't figure that one out. Label is 1. Where do you click to obtain a diagram to see a bubble point or dew point for a binary mixture? Well, as we know from Dr. Ha's class, we use TXYs for those, especially for mixtures. And we actually only can do it for mixtures. So I would say under here, where it says binary, under the analysis, this is where we've been working a lot in this zone here. Pure is just binary with only one component. For you can see like what's the vapor pressure of water given a range of temperatures. That's what pure does. Binary is usually our TXY, PXY diagrams. Mixtures, I can't remember what they do. Solubility curves, and so on and so forth. It's going to be the analysis tools for that one. Where do you click to move on to the simulation environment? Well, simulation. I haven't read these before. These are really nice. I hope the exam is just like this.
These are scary easy.
This is, yeah, it makes me like red herring.
It makes you nervous, right?
It's unbelievably easy.
Yeah, it's like the second exam we had, I hated. I thought it was awful. It was just so much math, so much juggling numbers. The first exam was just a lot of work to get like a program to run. This just seems just too good to be true.
I thought the first exam was the worst, man. I don't have the coding bug like you.
Well, I haven't taken so I took differentials in the second semester freshman year, and I haven't taken a formal math class since. So I almost couldn't take the derivative of the equation he gave us. It took me I would say half the time just to take the derivative. I'm not good at math anymore. I used to like it until I had like the worst math prof, known to man. So
yeah, that'll do it.
that kind of killed
Yeah,
it.
like that put you at a disadvantage because I'm taking DFQ right along with this class, so it's like fresh in my mind.
Yeah, and that's when you said that we're going to need to use Laplace transforms in control. That really scared me because
Scares me. Yeah, I'm not too good.
Like I know what they are, but I have like no clue how to use them like anymore. Like I know that they're a nice, easy tool to solve differentials, but I don't know like the steps to do it anymore.
Well, we'll take that class in our like senior year, so I'm sure that they'll spend like a lecture or two just like go refreshing our minds with the math.
Yeah. Where would you click if you need to specify electrolytes and their behavior? So as we've used before, electrolyte wizard, that's really it. Yeah, we can specify things like salt in our component ID, and the electrolyte wizard will pull that information for us and then add our ionic species as we need, as well as any equilibrium data we need for things like salt dissolutions and such. But we actually have to use the electrolyte wizard if we want to do like a salt problem, because it gives us the correct solubility data from the databases. I found that they're like the difference between using the electrolyte wizard and not is like 4%. I think if I remember right. It was the solubility was off by 4%, which isn't like that big of a deal, but I mean it still is kind of like, well, why is it just a little bit off? So you have to use the electrolyte wizard if you're gonna have ionic stuff. All right, problem 3. That was, now let me just preface that was 15 points out of how many are these? Is this out of a 50 plus?
Out of 100 as usual.
That's 15% of your grade on this exam was circling a binary simulation and electrolyte wizard. That's amazing.
What does he mean by like circle it though? Like, do we have to print that out, or?
I don't know.
Because he did say that he doesn't expect all of us to have a printer.
I don't know what's gonna. I imagine he'll then make this so that, we can do it at home. This was an in-class exam, so I imagine he'll do something to make this more. I imagine it'll be like a pure multiple choice or some sort of like written response. I can't imagine there'll be these kind of things where it's like a label, because how would you do that if you don't have software for it? All right, same thing. Problem 3. Label as 1. Where do you find the Gibbs reactor? Well, we actually just learned that today. We're using reactors, so we just go under the reactor tab under the model palette, and we find it under there. Where would you click to add a temperature label to the streams? This is something we haven't really done too much in class. All you have to do to see things without actually having to go into your stream results is actually just click here, temperature. You can also do things like pressure, flows, and all sorts of things, and it'll add little icons above them with each stream. So let's say I don't want to go in the feed every time in my stream results every time to see what the temperature is. I can just put the temperature stream results check marks, click it, and then it'll say the rounded temperature. It'll give you like if it's like 98.75, it'll give you just like 99. But it can help a little bit. But that's where you would click is temperature. Circle what stream you can specify. Well, we know that we only can specify feed streams if we don't do some fancy work behind the scenes. So feed. Where would you click to specify the flash unit? Well, there's actually 2 answers to this one. You could either double click on flash. Well, there's 3 answers. Double click on flash, right click on flash, and then click input. Or on blocks under flash input here. That's the same thing. There's multiple ways to do it, and all of them are the exact same. Where would you click to start a sensitivity study? Well, that is under model analysis tools, sensitivity. That just says it there. That's really it. That's the entire exam.
God, I hope it's just like this.
Oh, that's so nice.
That'd be a dream come true.
I thought this exam review would take at least 40 minutes, knowing how his last exams went, but this is a dream. Well, I think that's kind of it. Yeah, I mean, the only one I would ask him about is there was one that I was curious.
5.
I think it was number 5.
Yeah, 5. Yeah, this I'm not really sure what this he means by this. The wording on C. Again, I think he means to say only steady state, like the simulation environment for the entire software, not just literally the simulation like tab. I would say B, but I would definitely like in class ask him what he means by simulations, where feed streams, and etc. But do you guys have any other questions? I mean, that's if you've just been using Aspen, it seems pretty straightforward. You know, basic operation. You know, specifying stuff, and I was expecting this class to go a little more in depth with like make a process to do this, you know, design stuff, and I guess we'll do that in design. But I definitely was expecting at least a little bit to like make a process if you feed X, Y, and Z to split them up into, you know, certain mole percents or some like design aspect to it, not just run a simulation in these conditions. What do you get? So I guess on that point, I'm a little saddened, but I guess we'll get there down the road, and I imagine I'll, you know, mark my words, it'll probably be way worse than I could ever wish. So
I will be.
Yeah, that's it, guys. That's all I got for you. I'll throw this up on YouTube as well. This is like a quickie thing, so that's it. That's all I got. I'm gonna hop off. I need to do some homework. I have a paper to write that I really don't want to write, so I need to give myself like 5 days to do it.
All right, sounds good. Thanks for the help.
All right, no worries. Take care, guys.
See you, Gunnar.
You too.
Yeah.
Thanks so much. Bye.